Now I would like to leave the floor to Liam Nolan, who will open the session today. Let me just first introduce him very briefly. Liam Nolan has been president of MARCOGAZ since June 2022. And he also serves as the head of technical competency and standards at Gas Networks Ireland. He has background in gas distribution, network design, construction operations, market opening, and health and safety. And he has held several relevant roles in the gas sector, and he also represents Ireland in the International Gas Union Council. So Liam, welcome, and over to you.
Thank you, Virginia, for the introduction, and welcome everyone to the 4th edition of the MARCOGAZ Tech Forum. This time we're coming to you during the Hydrogen Week here in Brussels. Our primary objective in this webinar is to delve deeper into the findings and implications of the recently published MARCOGAZ study on hydrogen readiness and costs. The study sought to provide clarity to the status of the European midstream and downstream gas infrastructure regarding its hydrogen compatibility. The study aimed to estimate for each level of hydrogen acceptance the related costs of hydrogen admission into the existing natural gas infrastructure and end-use equipment in Europe. The study has been undertaken in great detail to shed light on the challenges and opportunities associated with repurposing and retrofitting the gas infrastructure. Our Tech Forum brings together many industry professionals, policymakers, researchers, stakeholders involved in the energy sector, for what will again, I'm sure, be an interesting and insightful discussion. The MARCOGAZ approach to the study involved collecting data from European gas operators and stakeholders and considering various hydrogen concentrations in natural gas mixtures. The results were illustrated in an infographic showing the extent to which natural gas assets can accommodate hydrogen blending and up to 100% hydrogen. The infographic was initially released back in 2019 and was updated again this year in October. And it provides a current snapshot of the natural gas transmission and distribution systems readiness for hydrogen integration. These studies were the result of collaborative efforts of many experts through the MARCOGAZ working groups and committees, and is literally taking years of dedication. We also collaborated with other associations and organizations in the gas industry, demonstrating a collective commitment to advancing understanding of hydrogen integration. To demonstrate the ongoing efforts by midstream and downstream gas operators to decarbonize the gas system, during this event, we'll have the unique privilege of learning from Fluxys, the Belgium TSO, and from Flowine, a gas DSO in Portugal. I encourage you all to actively engage with our expert speakers here today at the Tech Forum by posting your questions in the chat section. We've allocated some time for a Q&A session towards the end, which Anne-Sophie will moderate. In MARCOGAZ, we are focused on doing what we can to achieve climate neutrality objectives by 2050, to collectively build a path towards a more sustainable and hydrogen-ready future for the European gas industry. We hope that the publication of this report and this study can make a contribution towards achieving those objectives. So once again, thank you for your participation, and a particular thanks to our presenters here today at the Tech Forum. Thank you.
Thank you, Liam, for your the opening of the session. Now, dear participants, let me briefly introduce our first presenter today, Gert Müller-Seeding, who will be sharing important insights from the recently published MARCOGAZ study, which has the name of this webinar, so Cost Estimation of Hydrogen Admission into Existing Natural Gas Infrastructure and End Use. Let me introduce him briefly. Gert has been part of the DBI group since 2002, where he has led the advancement in hydrogen integration, smart gas grids, power to gas, and sustainability strategies in the gas industry. He is present in several industry associations, and within MARCOGAZ, he is co-chair of the Task Force Hydrogen, where he has promoted collaborative research and knowledge exchange on this critical topic of hydrogen that we are discussing today. So Gert, please welcome, and the floor is yours.
Yes, thank you very much for this very kind introduction, and thank you all for joining our MARCOGAZ Tech Forum today. Yeah, well, how I could start? Maybe with all of the good things come to those who wait. And unfortunately, you have to wait for quite a long time. But now we are here with the report on the costs for the hydrogen admission to the existing natural gas infrastructure plus end use. And yeah, we have prepared a little agenda for the presentation. And at the beginning, I would like to share with you briefly the goals we had in our minds about 3 years ago. I would briefly introduce into the scope and who was involved in preparing everything. I would like to try to explain as good as possible the general approach of the methodology we have applied. And I will give examples for the asset volume approximations we did, the mitigation measures and how we selected them, and finally for the cost estimation. Based on these little examples as an insight, we will have a look at the results of the study, the key findings, and finally we look at the infographic that has been updated in the frame of this work. Well, so I hope that you like the agenda, and I also hope that you can hear me well. And I would say, let's start. Rules of the study. What we had in mind when we started this work, and it was mainly to give a deeper insight into the infographic that has been issued in 2019, especially to understand better the mitigation measures that needs to be taken when we add hydrogen to the existing gas infrastructure, and including the end use. End use, this is very important here, is focusing on domestic and commercial appliances. The industrial appliances are not included because they are so individual that we are not able to consider them as a group and to define the mitigation measures and approximation of the costs connected to the mitigation measures. So very important, end use is including domestic and commercial appliances. We had as a goal to find out the mitigation measures and the related costs for a hydrogen admission of 2, 5, 10, 20, 30, and 100 volume percent of hydrogen. And finally, of course, the update of the infographic was one of our goals. So far about the goals we had in mind. Now let's have a look at the scope. The infrastructure segments we have considered are gas transmission, underground gas storages, gas distribution, pressure regulating, and the end use. Again, domestic and commercial appliances. What we have used, so the information that have been evaluated and digested for the study, that were as a major group MARCOGAZ documents and statistics. We looked at well-known reports as the 10-year net development plan and of course pertinent studies as the hydrogen backbone, the 11th EGIC report, and so on. We also used project results from other projects as TIGA. I have seen Jean, you here in the room. Thank you very much for providing this valuable information. That was extremely helpful. And what else? Many contribution of the task force members, but not only task force members, but also information that we gain from bilateral expert interviews. And I have also seen quite some of the experts that helped with their knowledge here as well today in our tech forum. So thank you for your support and thank you for being here. We focused on the infrastructure itself. So we did not focus on the systematic or the system aspects. For example, if a pipeline is changed from the natural gas service, for example, to pure hydrogen service, then we know that there is a decrease of capacity. It's not much, it's about 15%, but in some cases, these 15% less capacity could lead to the situation that not sufficient capacity is available anymore. And that's a very individual case or an individual situation, and this needs to be addressed by the grid operators itself. We only focused on the hydrogen on the infrastructure itself. This individual situation is also considered by the statement of NSOC, what is also included in the report. But it's important to know that here, on a very general level, we cannot deal with those individual restrictions or situations. Yeah, who was involved? The MARCOGAZ working group gas transmission. Thanks to all of you. The working group underground gas storage, the gas distribution group, utilization, Eurogas was involved, NSOC was involved, and a lot of further experts were involved. So that's the overview of the scope and how we focused on our topics. What is the basis, the knowledge basis, and who was involved. Let's have a look at the methodology. We have introduced a general methodology, what started with the quantification of the assets we have in Europe. So that was the very first part of the work to see how many kilometers of gas transmission distribution pipelines, how many valves, how many boilers, and so on are installed in the infrastructure. The second step was to evaluate, are those infrastructure elements suitable to accommodate hydrogen, and to what extent? And if we exceed certain limits, do we need mitigation measures? And this has been done for all the elements considered and for the hydrogen concentrations you have seen at the beginning of the presentation. So beginning with 2% up to pure hydrogen. As the third step, we considered, okay, there are actions necessary for certain hydrogen concentrations. There are mitigation measures necessary, and we estimated the costs for those single actions. And the cost for those single actions for each of the hydrogen concentration considered, they have been added up to total costs for the transformation of the gas infrastructure, including the end use. That was the general approach we followed. But yeah, the difficulty is always in the detail. So when we started with this very first point here, the quantification, we have assumed that a number of the pipeline lengths, the installed compressor capacity, the valves, etc., that could be found in the statistics of the associations and maybe in other documents. But that was not completely true. So we started to find solutions, to find workarounds, how we can quantify what we have installed across Europe. And that we can now see as a few examples here in the asset volume approximation. As one of the examples, I have here the asset volumes from the gas transmission system. And it was relatively easy for the length of these steel transmission pipelines that are operated. You can see them here in the first line. And you can also see here the source, what we have used. Then in the technical discussions within our task force, we understood, well, there's a difference between younger and older pipelines, especially when we consider the wells that has been prepared in the field. Older pipelines, they were less automated and the non-destructive testing was not so elaborated. And therefore, the probability that we have cracks or crack-like defects in the circumferential wells are higher for older pipelines than for younger pipelines. We were able to elaborate on a year, 1984, has nothing to do with George Orwell, where things have changed in the capabilities of producing high quality wells and to have a very well-developed non-destructive testing. And based on this year, 1984, and with the help of the JAGIC report, we split it up the length of the steel transmission pipelines. And by this measure, we were able to distinguish between younger and older pipelines, which is later important for the mitigation measures and the cost estimation. Regarding the valve stations, we recognize that it's not possible to, or it was for us in the given time frame and in the stage of the process, not possible to find a complete figure of valve stations that are installed in the European gas transmission system. And in order to find a solution, we used all the information we received from the partners, and then we calculated a specific value. And an average distance between the valve stations, and this average distance has then been extrapolated on the European case. And this way of finding specific values based on information available and extrapolation to the complete European system that has been applied quite often in order to have a profound basis for the next calculation steps. And you can always see that here in the very right column to see where extrapolation is mentioned. There we applied this approach. Another example, just that you can build up a feeling how we did all the different steps, is here the gas distribution pipes. Here we had quite a good basis on the based on extracted from the MARCOGAZ statistics to create a very up-to-date list with the pipeline lengths of the distribution system across Europe, including the Ukraine. And quite interesting to me, in the Ukraine we have the second largest gas distribution system across Europe. That's quite impressive. What else? Little acceleration that you can see it a bit better. And regarding the underground storages, which are quite complex facilities, we elaborated in the first step the different type of underground storages we have across Europe. Then we calculated, or we developed an artificial weighted average of the different storage types. And based on this weighted average, we then assessed how many facilities or components we have on such an average underground storage. So the number of turbo compressors and piston compressors has been estimated based on quite a lot of discussion with experts and reports. And we did it for the engines, for the needed coolers, for the separators, the gas drying facilities, for the field pipelines, for the wellheads, and everything what you find on key elements on such an underground gas storage facility. So here a bit a different way of working than with the pipeline systems, because here the complexity of the infrastructure forced us to develop such an average group. And we applied the same for the gas pressure regulation systems. I do not have an example here, but you can read it in the report. There we developed 4 categories. So up to 5 bar, 5 to 16 bar, larger than 16 bars and larger than 40 bars. And behind each of the group, again, technical setting with a number of trains, a number of regulators, filters, measurement systems was behind the group, and based on the number of the group and the distribution, we were able to calculate costs in the next step. But it was not the next step, it was the step after the next step. The second step was the mitigation measures. Relatively easy in comparison to finding the asset volumes. This was based on a lot of discussions with the experts, with reading quite a lot of reports, and finally we developed tables like this here, where for a certain hydrogen concentration here for the group from 2 to 10 volume %, and for the two groups of the pipelines, a risk assessment was considered as a mandatory measure. And of course, later the risk assessment is connected to costs. If you exceed the 10 volume % in the system, based on the ASME codes and other codes, further action is needed. And we developed that an inline inspection, which is a combined inline inspection for metal loss, but also for cracks and crack-like defects, needs to be applied if we go for hydrogen concentrations greater than 10 volume %. But only for the pipelines that are operated in a dynamical way regarding the pressure swing. And after the inline inspection, we have assumed, yes, there will be defects in the systems, and those defects needs to be repaired. So here it still looks quite the same for both the old and the young pipelines, but this will change later when we look at the costs. We did the same with the underground storage facilities. I have here a little enlarged table. So a lot of assumptions were needed for the different concentrations. And here again, there was discussions with the working group of the underground storages within MARCOGAZ. And finally, we were able to have costs behind the mitigation measures. And the third step was then the cost estimation. The cost estimation here for the pipeline, the transmission pipelines, you remember, it was an inline inspection here with €0, the risk assessment with €0, but there is another part in the calculation which considered costs for documentation, because people not always have all the information on the pipelines and also the fittings and the valves by hand. So costs were allocated for that, and also for applying a risk assessment. For the inline inspection, it was assumed that the costs will about €23,000 per kilometer and €50,000 per repair. And for the older pipelines, it was assumed that we will have more needed repair in comparison to the younger pipelines. And therefore, at the end of the day, you see different costs for the combined number euro per kilometer. We did the same with the underground storage facilities and with the gas pressure regulation stations and the gas distribution systems. And I hope that based on this explanation, you got a feeling how the costs were estimated, and that it's not just an estimation by a rule of thumb. We looked into technical details as much as possible, and we tried to find as precise as possible information on the installed infrastructure elements, including the end-use devices. Then I would say, let's have a look at the results. Maybe this is one of the most interesting tables in the report. You can see here the adaptation costs in comparison to the concentration of hydrogen that might be added to the infrastructure. And you can read the table in a way that here you find the costs if you add 2%. The costs here explain an addition of 5%, but it's not the difference between 2 to 5, it's from 0 to 5. And here again, from 0 to 10, from 0 to 15, and so on. So this is always this, starting from now to certain concentration. We calculated the total number of costs, not the total number, but the percentage of about 19% if we change from pure natural gas to pure hydrogen service. And these 90% of cost is in comparison to a new built infrastructure for hydrogen. So if you have to choose to build a new infrastructure, then you would have to pay 100% of the costs. If you refurbish the existing one, you arrive at 19%. This 19% is only the infrastructure. If we add the end use, domestic and commercial appliances, then we see about 40.5% of the costs for the new build infrastructure. And here, you can see again the basis. This is always related to a new build infrastructure. And in the lines here, you can see the costs for the different infrastructure elements. The next slide, you can see again, the summary. So this is more or less those two lines here, but a little bit of rounded figures, and again as a little graph. And I think it's relatively easy to extract from this graph here that up to 20 or even 30 volume percent, we have relatively low costs for adoption of the existing gas infrastructure. This is good news, but more in the key findings. The key findings, are four. If we add 10 volume percent of hydrogen to the existing gas infrastructure, then we see less than 1% of the capex costs for a new build infrastructure. That is extremely low. So this is a strong point for blending. I know that blending is discussed quite diversely, and it may has also some disadvantages. But if we look only at the figures here, then that is, for sure, a good opportunity for ramping up the hydrogen economy across Europe. And I personally think that's a very important opportunity to put us here in Europe in a good position regarding the production of electrolyzers and starting the hydrogen infrastructure here in Europe. If we consider higher concentrations, they might be more interesting for the gas distribution systems, but here it's calculated for the complete infrastructure. Then we see costs of about 10% of the existing of a new built gas infrastructure. So 1/10 of a new infrastructure if we add 30% of hydrogen to the existing system. Still quite low figures for a big advantage. And if we talk about pure hydrogen service, then we see the 20% for the infrastructure, or the 40.5% for the infrastructure plus the end use. That was only figures on costs and transformation activities and efforts. But of course, we have also a question of how fast we can be. And using the existing infrastructure, I'm quite sure that everyone who is involved in projects know that we can accelerate the process very much if we use existing infrastructure, because then we have much less of the planning activities. We have significantly reduced regulations and also issues with communication to the public. So This is another advantage what was not calculated here, but it's mentioned in this report as well, that we should remember this good point. We had on our agenda that we have a look at the infographic on the H2 tolerance as well. So this is an updated version, as you know, and it's very important to understand the legend, which you can see here in the upper part of the infographic. A dark green means there are no significant issues with this part of the infrastructure. A light green says yes, quite positive, but it could be that modifications are needed. It's not mandatory that modifications are needed, but it could be. The amber color shows us, yes, we can do that, but we know today that there are significant modifications necessary. The red color, as always, says, well, there's a problem, and this is where we use the natural gas, especially the carbon, as a feedstock. Well, if I need carbon as a feedstock and I decarbonize my gas, of course, then I have a difficult situation, and therefore feedstock is red. Gray means we have not sufficient information. Gray does not mean that is not feasible or impossible to do it, but not sufficient information. And these sprinkled or stripes green here says there are some conflicting references. So some references say yes, it's possible. Another one says it's not possible. If you look again at the infrastructure as a whole, the infographic as a whole, then we can see up to 30%. That's quite a high level of blending. We see a lot of dark and light green. We see also some amber colors where we know, yes, significant adaptation is necessary. For example, here for the process gas chromatograph. But in general, this is very good news that the infrastructure as a whole in general is capable to deal with hydrogen concentrations up to 30%. To go for higher concentrations of blending is not very probable or not considered as a very interesting option. And therefore here the pure hydrogen is again very interesting. And also here we see a lot of green, but also some gray areas where we just need further investigations if the infrastructure that is installed right now can be used as it is for the pure hydrogen service. For example, for the filters, we were not able to find sufficient information to have a pertinent basis of sources to give here an answer. There are some further areas where we need more knowledge, and nevertheless, it's quite well investigated right now, thanks to the research, development, and testing projects of the last years. Finally, I would like to give a little insight of the number of hands or brains where the report went through. We developed after more than 2 years of intensive work a draft version of the report, and this has been distributed to the working group gas transmission, storage, distribution, and end use, and of course to the task force H2 itself, to ENSOG, and to Eurogas. In total, about 130 people received this draft version. The draft version was also discussed in the MARCOGAZ Standing Gas Committee Standing Committee Gas Infrastructure meeting in April, so quite after issuing the report, and the feedback has been digested, and we issued a final draft version of the report in July this year. And again, the whole group here received this report, and again we received quite some remarks, so thank you. for supporting us here. In total, about 500 remarks have been processed. And for example, in the cooperation with NSOC, well, we had a very intensive exchange. And yeah, we also processed then the remarks in a separate version of the report in order to provide best possible results. What we have learned from the findings, I would say using the existing infrastructure for hydrogen makes sense. It supports the energy transition, and that's with quite low costs, and that's for me personally the major finding of the report. I would like to say thank you to all who have supported that this report is available now. I cannot list them all because then I would need quite some time here. But as I see here in our group, a lot of people who supported the report, thank you. It was a great pleasure to work with you. It was a pleasure for the complete Task Force Hydrogen to prepare this piece of work. And if you have challenges in the operation of transition, then maybe the verify tool, and you can see here the address, may help you in this very important task. For the time being, I say thank you for listening.
Positive impact in the decarbonization process of the industry. Also, to remind everybody here that the full report is available in MARCOGAZ website, so marcogaz.org, for everybody that wants to consult it or read it. It's there. We will now hear two real-life examples of a TSO and a DSO on their projects and efforts towards the decarbonization of the gas grid. Let me first introduce you to Steven van Kijkenberg, who will speak today about Fluxys as the Belgian TSO on the way to decarbonize the gas system. Steven has 25 years of dedicated service at Fluxys. He is an experienced engineer who has exercised leadership in key divisions. And he also initiated the H2 and CO2 program at Fluxys in 2020. He currently serves as the head of technical management at the Fluxys business unit, NextGrid, where he focuses on developing infrastructure to facilitate sustainable and efficient energy ecosystems. So, Steven, welcome, and please, the floor is yours.
Yes, thank you, Virginia, for the introduction. And thank you to give the opportunity to Fluxys to present what we are doing in the domain of decarbonizing the gas grids. Perhaps let me start with a short introduction on who we are. 4 facts about Fluxys. We are a fully independent energy infrastructure partner, headquartered in Belgium, but also a presence in other countries in Europe. But not only limited to Europe, also some positions in the South America and the southeast of Europe. A purpose-driven company focusing on the energy future, and that's also completely integrated in our strategy. Where the focus is the green transition. We want to be the essential infrastructure partner for the future, which means that we are evolving from a monomolecule operator to a multi-molecule operator. And that's also represented by the 3 figures on the top of the slide. Where we want to emphasize that by 2030, the target is to be able to transport through Belgium 30 terawatt-hours of hydrogen, but also 30 million tons of CO2. So that's all already indicating that we are no longer attached to one single molecule for the future developments. If one wants to decarbonize, it's always good to have a look at the starting point, and there is a starting point, of course, for Europe. But on this image, you can see the starting point for Belgium, where the total emissions on a yearly basis account for approximately 100 million tons of CO2 emitted by all types of activities highlighted at the left-hand side of this image. The target, of course, is to evolve to zero emissions, and that's why we presented at our industry, because industry is our first focus group, which account for approximately 40% of the emissions in Belgium. We presented to them a double solution, and we want to evolve from natural gas to also an offering for transport of hydrogen, but some companies are not able to decarbonize by using synthetic methane or hydrogen. They will still have CO2 emissions, and that's also the reason why we incorporated as from the start the option to also offer CO2 transport through our infrastructure. And that makes us saying that we are going to evolve from a single molecule operator to a multi-molecule operator, which means that transport of at least 3 molecules will be the case in the future. And I will come back on the interest we received from the market on doing so. In parallel, our technical colleagues had also a look at our existing network, and I think that perfectly matched with the previous presentation. And we came to the conclusion that we can state that almost 100% of our pipelines is repurposable, or for CO2 transports, of course, in gaseous form, or to use it in hydrogen. And as I explained in the previous presentation, when a natural gas system needs to be transformed to a hydrogen system, some equipment needs to be replaced. So we highlighted here some main topics: valve replacement, and adaptation of metering station, of course, and also compressor units. We take into account that we need to reconstruct them if needed on the hydrogen system. And of course, to comply with the other type of molecule, there has been done a reverse engineering on the existing infrastructure to define the operating conditions under which we can transport hydrogen in a 100% hydrogen network, under which operating conditions we can repurpose our actual natural gas grid. So those data is available. We have it done for all our pipelines. But of course, there is the availability of the infrastructure, because the natural gas grid is for the moment at almost full load in operation. So the repurposing will only take place in a second phase, where we will observe a decline in natural gas consumption. So the first wave will be mainly new constructions. I already mentioned that we are in close contact with the industry. We started to have a look where the emissions in Belgium are located, and then I'm talking mainly about the industrial emissions in Belgium. And then we observe naturally that they are present in the portal areas around Ghent and Antwerp in the north of the country. And you can see the dots on the screen with the industrial clusters in the south of the country. And we did a kind of, or we are still in a kind of open season process to interact very intensively with the Belgian industry in order to get information from them, who wants hydrogen, who wants CO2, and what are the volumes and what are the timelines. And we clearly wanted to break the chicken and egg dilemma, and that's also the reason why we proposed to the market a future grid for hydrogen and for CO2. We reached out, we got some feedback from the industry, we incorporated in our plans, and then we published infrastructure proposals, info memorandums. They are all available on our website. Also, product specifications are available on the website, operating conditions as well, and all that to evolve step by step to a more binding setup. And that's a process where we are in right now. And so it was from completely non-binding, and we want to have some binding contracts in the coming period. For the moment, we are a bit in the mixed zone, where we are doing and delivering feasibility study and giving feedback to the industrial parties on when are they connectable to the future grid, what will be the commercial model that we want to set up, and also an indication on tariffs. All that, of course, in line with the Belgian hydrogen strategy, which has a focus on 4 key pillars, as you can see on this image. And we as Fluxys are fully engaged in the two boxes with a rectangle around it. So Belgium has an import and transit hub, just as for the natural gas system. We need to import a lot of energy in Belgium, so we will also foresee import facilities for hydrogen, complemented with some local production as well. But import will certainly have its place. And we are always looking at the network development in a spirit of connecting it as soon as possible with neighboring countries, just to be able to create a robust hydrogen market in Northwest Europe. And of course, coordination and partnerships are key to make it a success. What is our long-term view for the Fluxys hydrogen network? And that's the network that you can see on the screen, with the openness to the surrounding countries, being it France, Luxembourg, Germany, or the Netherlands, but also at the import side. You can see that imports from abroad will be made possible by foreseeing and developing import facilities in Antwerp or in Zeebrugge. That's the long-term view, and all our investments that will contribute to this long-term view are, of course, with the development taking into account short-term needs, but also taking into account the long-term needs to come to the optimal solution. And if you keep this map in mind, then I can show you what will be the first development, our phase 1. You can see that it's 1 or 2 parts from the long-term perspective that will be constructed, and it will be operational by summer 26. So that's for infrastructure development, rather short time notice. So we are putting everything in place to make it happen. We are in the phase of permitting to obtain the permits to construct those new hydrogen pipelines. It will be around 150 kilometers to be operational by summer 26. The phase in the middle, at the end of the decade, will connect the initial investment. We'll connect the two early developments with each other, but in the context of establishing a connection between the portal areas and the German area, where in the first phase a connection between Belgium and Netherlands will be realized as well. So in that perspective, by the end of the decade, we will at least be connected with the Netherlands and with Germany. And then in the coming period, the network will grow step by step on a more market-based interest. I also highlighted the needs for import, and I think this is my last slide already. The needs for import, but it's also a combination between import and export, and that's also the reason why we are putting our LNG terminal in Zeebrugge in the picture over here, because we are convinced that on that location, not only LNG or synthetic LNG will be imported in the future, but also NH3 ammonia import will be made possible over there, together with cracking installations to inject the hydrogen into our backbone, and then the other way around. We will also collect and transport CO2 from Belgian industry, but also from industry nearby, to transport it to Zeebrugge and to evacuate it to permanent sinks in the North Sea. So that was in a nutshell and very condensed a bit development of our first steps in the hydrogen network. Thanks for your attention.
Thank you, Stephen, for your presentation. Let me now introduce our last presenter for today's webinar. He is José Cadela Pequeno, and he is Head of Special Projects at Fluin. It's the largest DSO in Portugal. He began as a process engineer at Gas de Portugal. José has played a central role in different industrial projects. And throughout his career journey, José has led initiatives such as technical coordination for multiple distribution companies, and has led as well the implementation of key asset management systems. So José, welcome, and please, the floor is yours.
Oh, good morning. I'm going to share my screen. Good morning. I wish, first of all, actually, Fluin wishes to thank MARCOGAZ for the opportunity to share its experience with H2 blending into natural gas. So I will, in the next 20 minutes, give you an idea of the issues and solutions Fluin found to develop the Green Pipeline project, which is a small-scale blending project. Fluin is a holding that controls 9 of the 11 DSOs in Portugal, operating more than 13,000 kilometers of network and supplying 1.2 million customers. Its shareholders are Allianz Capital Partners and Meet Europe, a Japanese consortium including Marubeni and Tolgás. The Portuguese government strongly promotes renewables, both in electricity and gas sectors. In what concerns gas, new legislation and regulation pieces began to come out in 2020. And up to now, hydrogen has been particularly focused, with the national strategy being published in 2020, also one of the earliest in Europe. Strong funding programs were put in place, and an auction for H2 purchase by the last resource wholesale company was announced. It was announced for this year, but because of the political situation, as you probably know, it will probably be postponed. We will see. All this attracted many promoters, and Flowen received from since 2021 technological partner of Flowen informed that Just10, a company that supplies services and equipment for energy management located in Seixal near Lisbon, had installed a small electrolyzer to pursue a project of energy backup systems based in fuel cells, hydrogen fuel cells, and was available in the meantime to supply hydrogen to Flowen to test blending with natural gas. The electrolyzer was capable of producing 10 cubic meters per hour of high purity hydrogen at 10 bar, using green electricity, partly produced with solar panels, partly purchased from the electrical grid. Flowen evaluated the grid next to Just10 and seized the unique opportunity of preparing itself to the expected surge of renewables in the gas sector. The project received the green light from the regulators in 2020. It was presented to the Portuguese Fund for Innovation and awarded 100% funding, including the cost of hydrogen. And so the Green Pipeline project had just born. This project is all about safety and service. Safety in utilization and in operations, and service concerning fair billing and continuity of supply. These two cornerstones influenced all our decisions about how to proceed. The overall concept and solutions were the object of a basic engineering study concluded in December 2019, identifying all risks and establishing all fundamental guidelines and options. I will now give you a quick overview of the most important solutions adopted, which often simultaneously address several of our concerns. Gas is a commodity, and users are usually interested in keeping it so. No one wants issues about its gas supply. So experiments tend to be not well accepted. Flowen had to convince the customers which are in the project that this was a safe project and had no costs to the user. To tackle this issue, communication is of the utmost importance. Flowen offered a safety inspection to the user premises and any related repairs, created a dedicated phone line capable of clarifying any doubt and help with the premises inspection scheduling, created a dedicated website, produced leaflets with the most frequent questions and answers, and secured the support from Seixal municipality, which has a close relation with its inhabitants. We had to chase one or two customers to do the safety inspection, but overall had no issues at all with the project acceptance by them. Choosing of the injection point had to be done carefully. Excuse me. Mixtures up to 20% of hydrogen are theoretically interchangeable with natural gas, but we were worried with the conditions in which customers, premises, and appliances were operating. Flowen wanted to make sure the pilot project was a success with no incidents of any kind. To address this issue, we offered the customers a technical inspection, which for us was a safety inspection, and any repairs necessary to bring everything to code. This offer pleased the customers and guaranteed the best possible technical starting point for the project. It must be stressed, however, that no appliances were substituted, since we had the objective of proving that current appliances were suitable to burn blends up to 20% in real current utilization conditions. Inspections were led by ISQ, a Portuguese engineering company, and the assessment to the installed appliance was done with the help of Bosch, which is the leading gas appliance seller in Portugal. Choosing of the hydrogen injection point had to be done carefully. Network around Just10 is meshed with the other networks to the left, up or down of this map. The chosen point had to guarantee an even mixture along the network, that only a restricted number of customers receives the blends, since we are limited to 10 cubic meters per hour. That all customers receive the same blends, even if with a time delay due to transit time, and that there was no mixing with the natural gas coming from the surrounding networks, which would raise uncertainty about which customers were affected and how to invoice them. The solution was to isolate a small network around a pressure reduction station. It's a pressure reduction station that supplies gas to all this network, and which was meshed with other pressure reduction stations around this network. We simply closed 4 valves so that this part of the network was isolated. And we decided to inject the hydrogen just after the pressure reduction station. So the connection of the pressure reduction station to the network was interrupted, and the mixing station was installed as a bypass to the original connection to the network. We also had to build 1.4 kilometer long hydrogen network or pipeline to deliver the hydrogen from GS10 to the mixing station. The isolated network, this isolated network has only 82 customers, mainly residential. We have 2 small industrial customers. It has only one feeding point, which guarantees the same quality for all the customers supplied in this network, and there is no chance of having an uneven distribution of hydrogen along the network, since we are injecting the mixture, and all this is supplied with the mixture. That would not be the case if we inject hydrogen for instance, closer to GS10, but in a different location from where we inject natural gas. A PLC in the mixing station controls hydrogen injection to the desired percentage with a cascade controller. It receives the flow rate, the natural gas flow rate from the pressure reduction station, and calculates the flow rate of hydrogen required to meet the desired hydrogen to natural gas ratio. The calculated hydrogen flow rate becomes the set point for the dependent loop that controls the modulating valve, so that the measured hydrogen flow rate meets the calculated value. We therefore directly control the volumetric ratio between hydrogen and natural gas. VOBI control was discarded because the natural gas quality also changes, and so does the VOBI index of the natural gas. We also discarded the control of the hydrogen directly, because that would require more analyzers. The station control algorithm controls also other safety features, such as the hydrogen line pressure, and use the calorific value of the blend as a redundant hydrogen mixture control. HACCP study was conducted by ISQ to validate the safety and control scheme adopted. To guarantee a thorough mixture of the natural gas and hydrogen, we use the static mixture. You have here a picture of the one we installed. There are other kinds. This was the one which was installed in this case. It's a simple and no issues piece of equipment. And in the case of hydrogen shutdown, it keeps the natural gas flowing and guaranteeing the service continuity, which was important for our customers. Admixing, as you know, admixing of hydrogen, as you know, reduces the gross calorific value of the gas delivered to the customers. So the determination of the gross calorific value is of utmost importance to the billing process. Flow-N adopted for this purpose a fiscal calorimeter placed after the static mixer. The equipment is reliable and proved very, very easy to operate. It measures the VOBI index specific gravity and calculates the gross calorific value continuously. Reacts very fast to the gas quality change and is fully automatic, including a weekly calibration routine. To use the gross calorific value measured at the station, the collection of information to the billing process had to be reviewed. Customers ceased being invoiced with the gross calorific value from the TSO that we receive from the TSO, which is the standard procedure everywhere else in the country, and started being invoiced with the gross calorific value measured at the station. Communications between the station and our central systems and the commercial IT system had to be reviewed, and so it had the commercial system to use this value instead of the values that came from the TSO. The station PLC acquires, which is in the mixing station, acquires the VOBI index, the specific gravity and gross calorific value and hydrogen percentage every second, and calculates a hourly and daily average of gross calorific values, which are then communicated to the commercial system. As mentioned before, gross calorific value is also used as an independent monitoring system for the blend. If the gross calorific value falls too much or too fast, it means we are injecting too much hydrogen, and the station will shut down hydrogen injection. This is important to guarantee the blend is safe to use. Fluence supervises the station and the hydrogen line condition 24/7 through our SCADA. You can see here the screen which was developed for this project for the SCADA, and which we plan to use for future commercial projects. Hydrogen line is automatically isolated if the pressure gets too low, which would mean, for instance, a third-party damage in the pipeline, or too high, which means that the pressure control at the outlet of GS10 is not working properly. The strategy was tested in the ASOP study conducted by ISQ. ISQ also conducted a ATEX study of the station so that it is built in compliance with these standards. The hydrogen pipeline from GS10 to the mixing station was built in polyethylene. This pipeline transports only hydrogen, so it's 100% hydrogen. The hydrogen permeation is higher than for natural gas, but it's perfectly acceptable. And we run a leakage survey routine with for hydrogen, specific for hydrogen, with no issues at all. MARCOGAZ infographic, and this is the initial version. Published by Task Force Hydrogen, was a good good use to support the solution with our regulators, for instance. H2 is authorized with THT before leaving GS10 to comply with the Portuguese regulation for distribution and guarantee easy detection of any leakage. Finally, we had to review operation procedures, both for network operation and customer field services procedures. All the personnel, both for network and for field operation. Field operations is in the operations in the customers' premises, were trained previously to the commissioning of the station and injection of hydrogen. So at this point, we are injecting 12% of hydrogen in the natural gas with no issues whatsoever. The station is working well, no issues also. Energy billing procedures run without issues, and the measured gross calorific value, which is being used in the billing process, substituting the TSO, raises no complaints, both from the customers or from the people from the billing control system, billing control process, which don't have to care about it. With this project, Floen was able to develop all the aspects under its own control concerning hydrogen injection, becoming prepared for future commercial projects. The first of these being scheduled for the second quarter of 24, where blend will be distributed to about 14,000 customers in a network that supplies Rio Maior and Caldas da Rainha. The project, which are two towns in Portugal. This project had more partners, but these 5 years were very important for the development of the project. Gesten, which is the hydrogen producer. PRF, that not only built the station, but also developed the initial concept that we formulated for the station. The municipality of Seixal for its support. ISQ for the several engineering studies and safety inspections in the customers, and Bosch for its support with the appliance evaluation in the survey that we did initially. So I will finish with a few photos of the real thing, the project. You have here the 2 pictures of the electrolyzer. It's a small McPhee electrolyzer. At this point, it was not in operation, so the leads are off. You can see the inside of the machine. You have here the buffer at the outlet of Gesten, which is a buffer with 12 cubic meters at 10 bar. And here you have the pressure regulation and authorization before the hydrogen goes to the network. So you have here the 2 very small pressure regulators, 2 pressure switches for high and low pressure, and the solenoid valve that cuts the hydrogen if the pressure goes outside the limits of these 2 pressure switches. And you have here the authorization device, which is we use the lapping system for authorizing the hydrogen. The station has 2 rooms, one to the left, which is the gas side, and one to the right, which is the control and analysis side. You have here the pictures of the inside. This was before it went online, so it was still under installation. And then you have here the station already with all the pipes connected. This is the static mixer that we used. So the natural gas goes in by this pipeline, hydrogen comes in by this pipeline, and you have the mixture that goes to the network on the other side. This is one more photograph of the calorimeter, and this is the control panel of the station. And it's what I have to tell you about this project. It was an interesting project, and I hope it leaves Floen ready to receive more projects and commercial projects of hydrogen blending. Thank you for your attention.
Thank you, Jose, for your presentation. We are heading now to the Q&A session, and I would like to then give the floor to Anne-Sophie Decaux, who will be moderating these questions and answer discussion, and also for her to give the final remarks afterwards. Anne-Sophie Decaux is Technical Director and the Head of the Industrial Performance and New Technologies domain at Gertigas. Her experience includes roles at the Gaz de France, where she led the research units and served as a delegated operator for the Paris Distribution Network, GRDF. She joined Gertigas in 2009 and has held several key positions, including Deputy Director of the Val de Seine territory and Head of the Gertigas Technical Division. Within MARCOGAZ, Anne-Sophie is also Chair of Gas Infrastructure. So please, Anne-Sophie, welcome, and the floor is yours.
Okay, thank you, Virginia. So, as you can see, we have a lot of questions on discussions on the file of discussion. I think that we won't have enough time to answer to all the questions. So I will take only some of them, and we will see how we can answer to the other. Maybe to begin with our last presentation, a question for José. What about the product liability of the appliance? Did the manufacturers of the appliance give any guarantees?
We discussed the appliances mainly with Bosch, since they, from the 82, there were 4 which were not in some way manufactured by Bosch. And we were assured that I remember you that these appliances were homologated after 97, and so they were homologated already with 23 with a mixture that already has 23% of hydrogen. This said, there is no formal guarantee from the manufacturers that the appliances, the appliances are not homologated for this mixture. They are homologated for natural gas. We also know, and the practice that we are getting is that the appliances do work with mixtures up to now with no issues.
Okay, thank you, José. A question for Gert. Now, Gert, you had a lot of questions regarding distribution sector. I see an answer, but questions, does the distribution sector have a similar template or asset management studies conducted by the team? Could you give us some details regarding distribution?
Yeah, well, at first, I apologize. I have not included so many examples in the presentation for the gas distribution system, but it's completely included. We did the same assessment of the asset volumes, the mitigation measure, and the costs for the mitigation measures. And finally, we calculated also the total transition costs. And this is explained in more detail in chapter 8.4 in the report. But in general, it has the same quality, the gas distribution part, as the other parts in the study. I'm not fully sure if that was really the answer or the right answer to the question. If not, then please let me know.
Okay, and for you, there is also questions regarding underground storage. The average cost of converting UGS to 100% hydrogen is interesting, but some countries have mainly aquifer and other mainly depleted fields. Is there a difference in cost depending on the type of UGS?
Yes, there is. I was desperately looking up for information to give a bit more precise answer, so a quantitative answer, but I was not able to find the right figures in the time. Yes, there are different costs because the infrastructure or the facilities on the storages are different. You have usually differences in the number of wells, therefore the number of field and length of field pipelines is different. Then the compression behavior is a bit different. So there are individual differences between cavern storages and depleted oil and gas field storages. And our aim here was to give an pan-European picture, and that's why we have used this weighted average of the different single types of the storages across Europe. But if you look for a national figure, then it needs to be considered what the number of the different types of the gas storages you have. So that was a suggestion to dive there deeper on the national level. but we were not able to initiate an investigation on that. So, in short, yes, there are differences.
Okay, thank you, Gert. We have also a question for Stephen. Stephen, if we are with us.
Yes.
Okay. Do you really think that repurposing natural gas pipes for the transport of CO2 is just plug and play? Aren't there any special safety regulations that have to be considered?
Yeah, of course, there is a risk analysis to be done. So the plug and play is a bit provocative, but it's not a transformation that will induce very high transformation costs, and that's mainly the conclusion, because our natural gas network has a design pressure of a maximum operational pressure for natural gas of 84 bars, and maximum pressure when CO2 is still in vapor phase is about 35 bars. So there is a huge gap between both, which makes it possible to use those pipelines also for CO2 transport. Of course, there is an exercise to do with permitting and all that kind of angles that need to be taken into account, and that's for sure.
Okay, thank you. And maybe another question for you. Who are Fluxys' key stakeholders to decarbonize the Belgian economy?
I think I mentioned the industrial clusters that have a need for decarbonization. So it are all the big ones in the Portal area in Antwerp, which is the top 3 chemical cluster in the world. So I think all the majors are present there. Also, one steel-making company, ArcelorMittal in Ghent, is very present in the Belgian CO2 landscape. And then we have some lime and cement industries in the southern part of the country. And I think those 3 groups are on industrial level the most important partners or stakeholders. Of course, on the level of how to establish value change, there you need to partner up with other TSOs, but also with the different governments. And in Belgium, we have a federal structure, so which means a central government, but also a regional one. And the competences are a bit everywhere, so we need to interact very closely with the government as well. So it's rather challenging, but step by step we are getting there. I hope that answers the question.
Okay, thank you, Stephen. Maybe a last question for José. José, if you are with us, what are the perspectives of protecting the natural gas users when the hydrogen percent goes over 2%? 2%.
Well, the experience that we got from this small project is that the customers do not perceive the hydrogen even with the 12%. We want to raise the percentage till 20. But in this particular case, in Portugal, the distribution will be allowed to distribute up to 10% mixture, and until 10%, customers do not have no issues at all with hydrogen. Residential, we must distinguish in between residential customers and industrial customers. We do know that we may have a problem with industrial customers and with the applications or equipment which is not prepared to work with a higher percentage of hydrogen. That is an issue which has to be discussed with the government and the regulators, since this hydrogen push in Portugal is led by the government. So we have now in place regulations and decree laws establishing that producers have the right to connect and have the right to inject. And we as distributors are preparing ourselves on the side of our, let's say, on what we can control, on how to distribute hydrogen on a safe way. For the residential customers and up to 10%, we do not expect safety issues, at least not for the majority of the customers, not very high safety issues. For the industrial customers, we do not expect safety issues. We expect perhaps some efficiency or even problems for the operating of the equipment, and perhaps the efficiency of those of that equipment, which is something that has to be addressed to the government.
Okay, thank you, José. So maybe the last questions could be for Liam. Liam, Barbara said, this is a significant study. What are the plans to inform the European Commission, national governments, and other policy-making stakeholders? Liam, I don't know if you are with us and you can answer to this question.
Thank you. Yeah, thank you, Anne-Sophie. Yeah, it's a very good question. This is, I suppose, is the start of that process. So we invited a wide range of stakeholders to the forum here today, including policymakers and industry stakeholders. So yes, we think that this study is a good contribution to the debate around the use of the existing gas networks with hydrogen. And so over the next months and over the next year or so, we will be engaging with our members and our members in their national countries as well, with policymakers and industry generally, to, I suppose, to leverage and take the benefit from the understanding that has been developed with this study. And may I just say, take the opportunity to congratulate all the working groups and experts and everyone that contributed to this study. And certainly in MARCOGAZ, we're very proud of what has been achieved.
Okay, thank you, Liam. So I think it is now time to conclude this webinar. As you, Liam, I would like to thank Gert Müller-Syring, who had led this study with Aurélie Carayol. And also a special thanks to all the many MARCOGAZ members and experts from other European associations who have contributed to this report. It has been a long, arduous process that required a lot of data, and thank you for all for that. So this estimation is a compromise. There may be different vision on certain topics, but most important is that gas infrastructure companies show, thanks to this study, that they are ready to adapt the gas infrastructure to hydrogen in order to respond to climate challenges at the best cost. Gas infrastructure companies are well placed to play a major role in the future hydrogen system, and not only with their existing assets, but also with their capacity to build, to manage, to operate networks with a high level of safety, and manage this last point. The safety is also crucial. As mentioned by Stephen, another topic is also the question of the CO2 produced, especially during the transition or even ultimately by the process of certain industrial sectors. The capture, utilization, and storage of CO2 is a solution for the protection of climate, and this topic could probably expand rapidly. So with MARCOGAZ and our sector, we have to deal to this topic in depth too. So coming back to the core issue of our webinar, thank you to Stephen and José for sharing the interesting and concrete vision from your countries. And maybe as a conclusion, I would like to raise that this work on the webinar illustrates how gas infrastructure companies throughout the gas chain and from many European countries can work closely together to share knowledge and cost estimation within MARCOGAZ Standing Committee Gas Infrastructure. And this is a big success and a big help to develop this future market and need for climate. So, last point, our study is available online on the MARCOGAZ website, and you can use it to communicate. So thank you all for listening. Thank you, MARCOGAZ staff for the organization of this webinar.
Thank you, Anne-Sophie, and thank you, everybody. The speakers, thank you once again for this insightful presentations, and thank you everybody that participated today to the event. We are available for if you have any further questions after the webinar. We are happy to assist you and to answer your questions, and maybe you want to suggest new discussion topics. We are always open. Thank you so much. We hope to see you in the next Tech Forum. This webinar and the presentations will be available in the website in the upcoming days. So thank you so much. Have a great day and see you next time.
Okay. Bye-bye.